All right, well, welcome everyone to our session here today on evaluating geothermal heat pumps, carbon, and the grid. You know, with the adoption of heat pumps and electrification, what impacts will there be on the grid, and what does it mean for you and your project? I hope you'll join us here for this conversation as we discuss the U.S. Department of Energy's Oak Ridge National Laboratories modeling analysis to examine the potential impact of mass geothermal heat pump deployment on the electric power system and associated carbon emissions. Before we get started, we always like to do our membership spotlight. And so this one is a congratulations to our member, Better World Builders, and their change agent energy auditor, Tom Tischler, who has recently achieved his certified green home professional designation. You can check them out over at the Better World Builders COMFOR for both services and inspiration. And you can learn more about the certified green home professional designation on the Green Home Institute website. You know, this is who Green Home Institute members are. This is what Green Home Institute members do. And so can you. Check us out at greenhomeinstitute.org/become a member. And thanks to one of our session sponsors today, Build Equinox. They're featuring the Serve 2 for housing and the Serve 1000 for schools. The Serves are demand-controlled smart ventilation systems which detect poor air quality and only ventilate as needed, saving energy and reducing overventilation. Now, with their new GeoBoost technology, as outdoor temperatures drop in the winter, energy collected with a soil heat exchanger warms outdoor air, boosting the Serve's heating capacity and heat pump efficiency. The colder it gets, the greater the boost. Now, during the summer, the GeoBoost pre-cools the outdoor air that also augments the Serve's energy capacity and performance. You can learn more about the Serve 2 and the 1000 and how they work with geothermal energy over at buildequinox.com. And before we get started, again, my name is Brett Little, and I am the education manager here at the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. This course, like many of our courses, is approved for multiple continuing education units, including our Certified Green Home Professional designation in Energy and Place. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license, and you can grab the Passive House code off of the follow-up email you get for attending or your certs at gutenbergcerts.com at the conclusion of this course. So with that, I'm going to hand it over to our speaker today to take us through this session on evaluating geothermal heat pumps, carbon, and the grid. Dr. Xiaobing Liu, welcome, and please take it away.
Thank you, Brett. And also thank you for giving me this opportunity to present my recent study. Let me start share screen. Okay, first let me introduce myself briefly. My name is Xiaobing Liu. I'm a senior R&D staff at Oak Ridge National Lab. Today, I'm going to briefly introduce one of our recent studies. This particular study evaluated the impacts of mass deployment of geothermal heat pump for building heat and cooling electrification in the United States. This presentation of three parts. First, I'd like to talk about the pathway for decarbonization, and then we will discuss our study, including the methodology and results. At the end, I will summarize the findings we get from this study, and also a few actions I think is needed to realize the potential identified through the study. This image shows the connection between the building and the grid, right? Building use lots of electricity for heating, cooling, water heating, or other appliance, electronic device. Even, the EV is charged in the building, right? The building is connected with the grid. So if we can change the energy consumption in the building, it will not only affect the emissions in the building, the energy bills paid by the building owner, it could also have impact to the grid, right? So I'd like to read a paragraph from the long-term strategy of the United States, pathway to net zero greenhouse gas emission by 2050. This report is published by U.S. Department of State and U.S. Executive Office of the President in November 2021. This paragraph vividly described the trend and the consequence of climate change. Let me read it. In the United States and around the world, we are already feeling the impacts of a changing climate. Here at home in 2021 alone, we have seen historical droughts and wildfires in the West, unprecedented storms and flooding in the Southeast, and record heat waves across the country. We see the same devastating evidence around the world in places like fire-ravaged Amazon, the sweltering urban center of Delhi, and the shrieking coastlines of island nations like Tuvalu. Right? This paragraph, the next paragraph, also pointed that this climate change is not only a potential crisis, but also could be an opportunity. It said, we are headed toward climate disaster unless we achieve net zero global emission by mid-century. We also know this crisis presents vast opportunity to build a better economy, create millions of good-paying jobs, clean our water and air, and ensure all Americans can live healthier, safer, stronger lives. Okay, now let's talk about buildings. Building contributes more than 1/3 of all the carbon emission in the US. So this pie chart shows, the sources of carbon emissions. For the building sector, in the building sector, the on-site combustion and the electricity generation for the use in building are the most important source of carbon emission. So to reduce carbon emission in buildings, we have to either eliminate the on-site combustion, or we have to reduce electricity consumption, or we do both. So electrification is not enough by itself to realize this decarbonization goals. Because if you only electrify, the space heating or water heating with a heat pump, it will increase the demand for electricity, right? And also the electricity generation also consume energy. If this energy is from those fossil fuels, it may generate more carbon emissions, right? So we need clean electricity if we really want to reduce the carbon footprint of our economy. But to generate this large amount of clean electricity to meet the higher demands of the electrification, we need to spend lots of money to build new infrastructures for renewable power generation, such as solar farm, wind farm. And we have to build long transmission lines to connect this remote renewable generation with the end use. In addition, the intermittence of our renewable energy requires batteries to buffer the demand and supply, right? The graph on the right-hand side is from the a recent report from DOE. This title of the report is Decarbonizing the U.S. Economy by 2050, a national blueprint for building sector. So this graph projects the required generation capacity from 2024 all the way to 2050. You can see why those coal-fired electric generation will be reduced significantly. The electricity generation from wind or solar and solar will be increased continuously, and the storage for electricity will also increase significantly. So the US government have a very aggressive goal to achieve net zero emission in our economy. It includes reduce greenhouse gas emission by 50 to 52% by 2030 versus 2005 level, and achieve the net zero emission economy by 2050. And also it requires decarbonization of our power system. The goal is to reach 100% clean electricity by 2035. In the meanwhile, we also need to make sure 20%, 40% of the benefits from this federal climate and clean energy investment will flow to disadvantaged communities to achieve the energy justice. The geothermal heat pump is a technology that can eliminate on-site combustion for space heating, and it also can eliminate the fossil fuel consumption for water heating. And also it can provide cooling. So it can work for both heating and cooling all year long, and the efficiency is higher than any other existing heating cooling technology because it utilizes the massive resource under our feet, the ground. The map on the upper right-hand side shows the contour of the undisturbed ground temperature across the US. You can see from this map that in most area, the undisturbed ground temperature range from 40 to 70. This temperature can make the heat pump run very efficiently to provide heating and cooling. And so you can notice this temperature range is much narrower than at the ambient temperature, right? That is the reason the geothermal heat pump can have higher efficiency than any other heating cooling technology. In addition to the efficiency aspect, this particular technology can be utilized almost in anywhere. Doesn't matter it's very hot or cold climate. You can still drill the holes, you still can run the heat pump. But the economy at very cold or very hot climate maybe not very good, but in terms of the function, this technology can still work there. And this technology can be utilized for many different buildings. It can serve the single-family houses. It can also serve large buildings like a hospital or a school. And because this system utilize a common water loop to connect the heat pump and the ground heat exchanger, this water loop can also be expanded to include many other resources, such as the groundwater or wastewater or a river or lake nearby. Those resources can all be utilized by those heat pump as a heat sink or heat source, so that they can let the heat pump to run at high efficiency. But if we only think about replace the existing heating cooling system with this geothermal heat pump, we may reduce the on-site emission, but we may have to use more electricity or build more power plant to meet the increased electricity demand, because we replace the existing fossil fuel heating system with this electric-driven heat pump technology, right? But our goal is to reduce the emission and also reduce the cost for decarbonize our grid. So we have to think about more than just replace the existing heating cooling system with geothermal heat pump. We have to think about how to reduce the thermal loads of the building, particularly for the air infiltration. So this chart shows the breakdown of energy use by components. We can see in both residential and commercial building, the air infiltration, which is indicated with this blue block, represent a significant amount of heating, cooling load, especially for heating load. This graph shows the thermal loads associated with the air infiltration is the largest component for the thermal demand of the building. And this infiltration, especially for residential buildings, it comes from many different places. Could be a small cracks in your floor or your ceiling, or in your door or your windows, or even some holes that penetrate your electric cables. Those small holes can let those outdoor air go into your building uncontrolled. And also the amount of outdoor air can go to your building is affected by the wind. It's also affected by the temperature difference between your room temperature and your ambient temperature. So in the wintertime, when you have strong wind, when you have large temperature difference between your room and your ambient, because of the chimney effect, you will get more infiltration of the outdoor air to your room. So it costs lots of energy to keep your room warm. So the average American houses leak 2 to 3 times more than the newly constructed houses that was built to meet the current building energy codes. According to ASHRAE Standard 6.2, the minimum required outdoor air ventilation for low-rise residential building is about 0.35 air change rate at this normal condition. But based on our large survey from existing building, most of the homes, their outdoor infiltration could be in the range, about on average could be 0.8. So you can see there's significant difference between what is needed for the outdoor ventilation, what is actually infiltrated from outdoor ambient. for single-family houses, the air leakage can be reduced on average by 25 to 30% just by air sealing. Those cracks or leaks at your doors or windows or roof or ceiling. So in this study, we account for this air sealing in single-family houses because this has become a typical practice for the geothermal retrofit. Those contractors, they include this air sealing as part of their geothermal heat pump retrofit package. Now, this study we address the following questions. First, what are the impact of mass deployment of geothermal heat pump, including air sealing in single-family houses, on the electricity consumption and on-site combustion related carbon emission in the building sector? Second, we also want to know how will this change in electricity consumption in the building sector affect the new infrastructure requirement and operation cost of our electric power sector. And also we want to know, will this impact reduce needed investment and the time for meeting the goal of economy-wide decarbonization? Furthermore, we also want to see whether this massive deployment of geothermal heat pump can help improve the grid resilience. Yeah, to answer all those questions, we worked with another national lab, National Renewable National Lab at Denver. We jointly developed first of its kind integrated building and grid modeling to assess the potential of impacts of geothermal heat pump. We start from building modeling. So Department of Energy had a set of prototype building models that represent many different commercial buildings and residential buildings for each different climate zones. We use this prototype building model, and then we replace the existing heating cooling system in this prototype model with a new ground source heat pump system. And then we calculate what is the relative difference before and after replace the existing HVAC system with a GHP. So with this relative difference, or this, we call it fraction factors, we can apply them to the energy use of existing buildings so that we can calculate what is the change in hourly electricity use in different buildings, in different climate zones, right? And then this input is utilized in the grid modeling. First, we run the power plant capacity expansion modeling to determine how much the power generation and what kind of power generation is needed to meet this changed electric demand. With that, we can calculate what is the needed new capacity for generation and the associated cost for the new power plant, for the transmission, for the storage, right? And this information, along with the change in the electric demand, are utilized as the inputs for the power generation cost modeling. With this, we can estimate the cost to run this power plant to generate this needed electricity, right? And also we can calculate what is emission associated with this power generation, along with the change in the consumption of fossil fuels at the building sectors, we can calculate what is the combined effect of carbon emission reduction in both building sectors and electric sectors. So to understand what is current energy use in existing buildings, we utilize the National Renewable Energy Lab's end use load profile database. This database presents all major end uses inside the building and for different building types within each county. And also it accounts for different climate conditions. So this database is generated using millions of building simulation results, and it includes hourly data generated with physical-based building stock modeling using the ResDoc and ComStock tool. And this result has been informed and validated against the ground truth. So this graph shows example of the predicted energy use profile during typical days in summer and winter in Texas for residential building. So you can see the simulation predicted result is presented with this stacked chart. And the meter data is indicated with this solid blue line. You can see the simulation result and the meter data matched quite well. So with this database, we select certain buildings that are applicable for geothermal heat pump. So this building will not include the mobile homes, all those the buildings that currently is heated or cooled with the district system. All the buildings either do not have heating or cooling, or if this building already have geothermal heat pump, we exclude them. So by excluding those buildings, we can account for 78 of the existing residential buildings and 43% of the commercial buildings. So you may ask why, the coverage for the commercial building is much smaller than the residential sector. This is because of, the coverage of this energy use load profile for commercial sector exclude about 36% of building that is small. That reason, we have a relatively smaller database for commercial building. So at the end, the buildings that we accounted for in our study for commercial buildings is relatively small. It's only 43% of all the existing commercial buildings. You may notice the building that are excluded from the energy use load profile are the smaller buildings such as churches or shops, repair shops or other small office. If those buildings are accounted for, the impact of the geothermal heat pump could be larger because those buildings, just like residential building, it can be conditioned with geothermal heat pump, right? The energy use load profile has lots of information regarding, the building characteristics, such as, the age of those building and the heating or cooling energy source for those buildings. So by checking all those data we found, natural gas is predominant fuel for space heating. That's for the residential and commercial buildings. But the electricity consumption for heating is also not negligible. So for residential buildings, about 30% of total residential floor space are conditioned with some kind of electric heating device, such as electric heater or air source heat pump, or maybe some small fraction of those buildings currently using ground source heat pump too. So that is important information we have to know. And in this study, we simulated ground source heat pump system that is commonly utilized in the US in residential or commercial building geothermal system, right? In our analysis, we assume that the geothermal heat pump is properly sized for each building so that it can provide 100% heating and cooling. So there's no any supplemental heating is needed. And also, I heard at the beginning of this meeting, Brett introduced a company talk about the ventilation. Yeah, ventilation, yes, is very important elements for the HVAC system. So for the commercial building, we simulated a distributed geothermal heat pump system. As you can see from this cartoon, the distributed geothermal heat pump system comprised many different water to air heat pump units at each room of the building, so that they can provide heating, cooling independently for that particular room. And all those heat pumps are connected through a common water loop. And then this common water loop is connected to a group of borehole heat exchangers. And you can also notice that in this cartoon, we put a dedicated outdoor air system on the roof. So this system will provide outdoor air to the return duct of this water to air heat pump inside the building to provide ventilation. So by this configuration, the heating, cooling operation and the outdoor air ventilation can be completely separated, right? So if your thermostat has been met, you can completely turn off your heat pump. And you just only need a small amount of outdoor air to go into your room. And we can also have some heat recovery to further reduce the thermal loads associated with this outdoor air ventilation. And in this, let me see. In this particular simulation, we use the geothermal heat pump units that have a typical efficiency values. So it can have a heating coefficient of performance of 4.0 and cooling coefficient of performance at 6.5. This number is at the typical rating condition, but in our simulation, this number will be varied depending on the supply temperature from this ground heat exchanger that is modeled with the most advanced modeling program for the ground heat exchanger. For the residential building, it's similar, but because residential building is small, so we only have one heat pump to provide heating and cooling for this entire zone through a central ductwork. And as I mentioned, the outdoor air infiltration can contribute significantly to the thermal demands of the building, especially for heating demand in cold climate. So in our analysis, we account for the air sealing so that we reduce the outdoor air infiltration to the minimum allowed by the AFRY standard. Okay, now let's see the results. First, this map shows the change of electricity usage in each county of the United States. This is annual electricity usage. The color bar indicates different percentage of electricity consumption savings. The red color means negative savings. That means you will use more electricity. But blue color means you will reduce electricity consumption on annual basis. We can see, except 2 states in the US, with those geothermal heat pump retrofit we just described in last slide, we can reduce the annual electricity consumption. And the electric savings is bigger in Southeast, where the cooling demand is high. So you may ask why the electricity can be reduced after you replace this fossil fuel with a heat pump for heating, right? The reason could be, counterintuitive, but if you think about the geothermal heat pump work for both heating and cooling, right? If you replace the gas furnace with a geothermal heat pump, you may increase your electricity consumption in winter, but because of the high efficiency of geothermal heat pump for cooling, so you may reduce cooling-related electric consumption in the summer. So if you combine them together for the annual electric consumption, you still can have savings in most part of the US. So we can also have some close-up look to see in some area, actually, even in the winter time, this geothermal heat pump retrofit, including this air sealing for single-family homes, can result in savings of electricity. For example, in the West Coast, for example, the Washington State and Oregon State. In this area, they have lots of hydropower, so they also have significant electricity consumption for space heating. There's this diagram on the left hand, this bar chart on the left-hand side shows the percentage of different energy sources for providing heating in this area. So you can see in lots of area, the percentage of electric heating is more than 40%. So in this area, if you replace this electric heating with geothermal heat pump, you actually reduce the electric consumption in the wintertime. And also you can reduce electric consumption in the summertime, right? So combine them together, you have significant electricity savings on annual basis. For the Southeast regions, in those areas, we can see there's also have significant electric heating. But mostly, I think this may be from air source heat pump because the ambient condition in those Southeast region is good for air source heat pump. But air source heat pump have relatively lower efficiency for heating, especially when temperature drop down quickly. So if you replace this electric heater or this air source heat pump, you can also reduce electric consumption in the wintertime. Plus, you will have significant electric consumption savings in the summertime. So this graph on the right-hand side shows the the difference of electricity consumptions in during the year at different locations. So if the value is positive, that means you have electric savings. But if you look at some other area in the Northeast, in those area, very small percentage of heating is provided by electricity, especially in this balanced area, 120 to 130. In this area, you can see in the wintertime, the values of the difference of electricity consumption becomes negative. That means, yes, in this area, yeah, more electricity will be utilized in the wintertime. But even in this area, you still can have some electric savings in the summertime because of the high cooling efficiency of the geothermal heat pump. So combine them together, in some area, you may still be able to get some savings or very slight increase of electricity consumption. So from the previous slides, we know the massive deployment of geothermal heat pump can save about 401 billion kilowatts hour of electricity, which is about 18% reduction from the current electricity use, from the electric use of existing building in 2018, according to that energy use load profile database. And this energy electric savings is big numbers, right? But obviously, this big numbers is just kind of give you the upper bound to see what is maximum potential, because these numbers come from assumption that all those applicable buildings are retrofitted with geothermal heat pump overnight. Then you will see, oh, compare with yesterday and today, you see those electricity consumption. But in reality, we cannot make those things happen so quick. But that just gives you a kind of a big boundary about what could be, right? And if we can make that kind of massive deployment of geothermal heat pump overnight, not only we save those electricity consumptions, but we can also eliminate about 4,747 billion cubic feet of natural gas equivalent. That means that it's count for not only natural gas, but also heating fuel, propanes. Because we can reduce this amount of the fossil fuels, we can reduce 342 million metric tons of carbon emissions. It's only just from reduced on-site combustions. And also from this graph, you can see different from the electric savings is mostly in Southeast and Texas area, which have very large population and high cooling demand. For this carbon emission reduction, you see it's covered all across the US, especially in those relatively cold climate in Northeast, Midwest, you get more. And also the percentage of on-site carbon emission reduction is also significantly high than the percentage of electric savings, because there's significant amount of natural gas consumption has been avoided by using geothermal heat pump to provide heating. Okay, so this is the the numbers that big to give you the boundary, but it may not be really a realistic number we can imagine for tomorrow or next year, right? It will take time to really retrofit all those buildings. So in our grid modeling, we account for 3 different scenarios of grid decarbonization. The first is base scenario. In that case, we just assume there's no any national carbon policies, just business as usual. There's no change in power generation. And the second scenario is called the grid decarbonization scenario. In this scenario, we assume 95% grid emission is reduced by 2035, and 100% grid emission is reduced by 2050. In addition to these two scenarios, we have another scenario we called electrification future study scenario. Basically, this scenario account for this grid decarbonization scenario, as described, in this yellow bar, plus some partial economic-wide electrification of end use, such as use air source heat pump to replace furnace in area that can allow air source heat pump to work, right? So in this grid modeling, we kind of distribute the maximum potential of the energy savings within the 30-year period from 2020 to 2050, assuming a constant deployment rate of those buildings. Each year we are assuming about 3% of buildings will be retrofitted. So within that 30 year, if each year is 3%, so you can reach that 100% maximum that all the applicable buildings, as I mentioned earlier, will be retrofitted with geothermal heat pump. In addition to this existing building, in this grid modeling, we also account for the new buildings during this time period. So we're assuming the same percentage of new building can be retrofit, can use geothermal heat pump, and same, energy savings we can expect it from this geothermal heat pump compared with the conventional HVAC system. So in this grid modeling, we account for this granular change of electricity consumptions because of this linear increase of geothermal heat pump deployment from 2020 to 2050. Now, let's see what's the impact to the electricity generation capacity. So this chart shows, both historical data of new power plant development in each year and the predicted new power generation capacity from 2020 to 2050. So you can see at the business as usual case, the new electricity generation will increase year by year because of the increased electric demand, because people use more electric device, right? But if we can deploy this geothermal heat pump in large scale, as indicated with this dash blue line, the required electricity demand can be reduced, right? So by 2050, we can reduce 173 gigawatts of new power generation. But if it goes to the grid decarbonization scenario, because grid decarbonization means you use more renewable electricity, but renewable electricity is not reliable. Not always reliable. It's intermittent. So that means to ensure reliable power supply, we need to have some other power generation standby, right? And also we need electric storage so that we can make use of this intermittent renewable power generation. So all those things will increase the total capacity of power generation, as indicated with, this orange, red bars on the right side of this pictures. We can see there's significant increase in the new power generation requirement in the grid decarbonization scenarios. And if you compare this solid yellow line and this dashed yellow line, you can see there is about 345 gigawatts reduction in 2050 after we realize the full potential of this geothermal heat pump deployment. And more electricity consumption and electricity generation capacity is needed in the electrification future study scenarios. Because in that scenario, not only you just decarbonize your grid, you also decarbonize the economy, such as use more, heat pump for space heating and use more electric cars. So economy-wide demand for electricity increased significantly. But the mass deployment of geothermal heat pump can reduce that required new capacity by 10 gigawatts in 2050. So the reduced capacity in different scenarios are different. From this graph, we can see in the base scenario, the reduction is kind of evenly distributed from all those different power generation, right? Because in that scenario, geothermal heat pump deployment only reduces the demand of electricity, right? So the grid will just proportionally reduce power generation. But in the grid decarbonization scenarios, because most of this power generation come from renewable energy, so you can see most reduction is from wind power, as indicated in this blue block, and this PV, and also this battery indicated with this pink color. The PV is indicated with the yellow color. And also there's some reduction in this hydrogen combined turbine power generation, right? This evenly distributed among renewable power, right? But if you look at it in the EFS scenario, the reduction mostly comes from wind power. Why? Our interpretation is, in that EFS scenario, it assuming lots of air source heat pump has been utilized to replace the furnace. So that means in the wintertime, you have lots of heating demand, an electric demand for heating, right? So if you can use geothermal heat pump to replace this air source heat pump, you reduce that winter demand. And the power generation in the winter most comes from the wind, right? So you can also reduce wind power generation. Now let's look at the transmission line. As I mentioned earlier, renewable energy, most of those maybe not really near your home. It's far. It's in the desert or in some rural area. So to utilize this renewable energy, you need this new transmission infrastructure. So for the decarbonization scenarios, it is predicted that by 2050, we need 258 miles of transmission infrastructure. But if the geothermal heat pump deployment can be gradually implemented during this time period, then in 2050, we only need 221 megawatts of miles of transmission lines. So that is 37 megawatts miles in transmission instruction reduction. This can be translated to about 24,666 miles of new transmission line, which can provide 1,500 megawatts of capacity. So that 24,000 miles of the transmission line is equivalent to you cross the continental US 8 times. In the EFS scenario, we can see that massive deployment of geothermal heat pump can have even bigger reduction in the needed new transmission lines. So in total, it's equivalent to 44,000 miles of the transmission lines, and it's equivalent to cross United States 16 times. And I just maybe show another example to give you some idea about how large this reduction is. In recent year, there's new transmission project is approved by the government. It's called Sunzia transmission. Basically, it's connect a large wind farm in New Mexico and send this electricity to the distribution station in Texas, so that in Arizona, so that they can supply this electricity to the West Coast. So this transmission projects need 550 miles of the lines and can deliver 3,515 megawatts capacity. So the reduced transmission infrastructure by deploying the geothermal heat pump is equivalent to 34 that Sunzia transmission project. For this Sunzia transmission project, according to the information I have, it cost about a few $1 billion just to build that transmission project. So in addition to the reduction in the needed transmission infrastructure, this massive deployment of geothermal heat pump, including air sealing for single-family homes, can also significantly reduce the cost of this clean electricity, right? So this graph shows the marginal system cost of electricity. It's a complicated term. It's not directly equivalent to the electricity price you pay, but it's effect or indirectly related to the electricity price you have to pay, right? So in the baseline scenarios, in 2050, the marginal system cost of electricity is about $49 per megawatt hour. But if you decarbonize this grid, get more renewable, get more transmission, more storage, then it will increase the cost of this marginal electricity to $83 per megawatt hour. But with this massive GHP deployment, you can reduce that cost by 12% in the decarbonization scenario. But in the EFS scenario, you can cut maybe by 8%. So, right. In addition to all those benefits, in terms of reduced capacity, reduced transmission, reduced energy cost, it also reduced emission, because the less demand for electricity means less combustions, for your power generation, right? So in the base case, if we deploy this geothermal heat pump, then in 2050, you can reduce the carbon emission by 23%, or 417 million metric ton. But in the decarbonization scenario for the grid, because the grid already take very aggressive measure to reduce carbon, so you add this geothermal heat pump does not really change much of the carbon emission. So, but if you look at this combined building and electric sector emission, you can see 33% of carbon emission can be reduced by geothermal heat pump deployment in base scenario, and 52% of carbon emission can be reduced in the grid decarbonization scenario if you combine both residential building sector reduction and electric sector reduction. So if we account for the accumulative carbon emission through 2020 all the way to 2050, the numbers is even more significant. So in the base scenario, if we deploy this geothermal heat pump to all these applicable buildings over this time period, we can reduce about 7 gigametric ton of carbon emission. Yeah, this number is about half grid decarbonization scenario, because in the grid decarbonization scenario, the grid is already clean. The emission is low, right? Same for the EFS, but in EFS, the building sector emission reduction is relatively small than the base case. It's because in the EFS scenario, it's assuming many buildings already use air source heat pump. So air source heat pump does not have on-site combustion. So if you replace, that means that smaller number of buildings that still use gas, then the geothermal heat pump retrofit will result in relatively small reduction in the on-site emission. So if we can combine all those benefits, in terms of reduced capacity, reduced transmission, reduced storage, we can see, the overall cost, for the decarbonize the grid can be reduced. In the base scenarios, the GHP deployment can reduce the cost of the grid, including infrastructure and operation cost, by $145 billion. In the grid decarbonization scenario, the savings is $241 billion. And we also did a small study just to evaluate whether this massive deployment of geothermal heat pump can improve the resilience of the grid. So we pick up a scenario of Texas in that winter storm in 2021. I guess you all remember during that time period, there's big winter storm, and it lasted about a week. And during that time period, lots of places experienced blackout because the grid just cannot supply enough electricity, right? So this graph, shows 3 lines. The green line shows the needed demand for electricity. The blue line, the orange line shows the actual delivered electricity by ERCOT, so that you see there's big difference between the needed and supply. So there's this result in blackout. But if we can implement geothermal heat pump in Texas, then the needed demand during that time period of the winter storm will be significantly reduced, as indicated in this blue line. So you see the difference between the blue line and orange line is significantly reduced. That means the outreach ratio can be significantly reduced. Okay, so let's just let me skip this summary because all the things we have discussed. Let's just talk about the actions. From this study, we saw there's big potential to reduce the cost for decarbonize our economy by deploying geothermal heat pump to all applicable buildings. But that analysis assuming that we need deploy 5 million geothermal heat pump per year. But currently, the deployment rate of geothermal heat pumps is less than 100,000. So there's a big gap. Right? How can we pick up the speed to realize this potential? I think this utility company investment in geothermal heat pump as the company's demand-side management and grid decarbonization effort is needed. I know some utilities already started this kind of investment. They invest some district geothermal heat pump system in Northeast. And also new business model and financing mechanisms are needed to encourage large-scale investment so that they can encourage massive production of the heat pump and also the installation of the ground heat changer. That may take advantage of economies of the scale so that maybe you can reduce the cost. And also the R&D and standard development is needed to simplify the design, installation, and investment so that people can easily implement the system with less cost. Okay, This is an acknowledgement of the study. I think I'm run out of time, so I just skip this and I stop here for question.
All right, thanks, Xiaobing. Yeah, let's jump into some of those questions now real quick. And before we get into those questions, just a quick reminder that yes, this session has been recorded and you can access the recording and and share it and help get the word out about it on our YouTube channel. You can either wait till it comes up in the next few days, or you can go there now, click subscribe, and get it instantly sent to your inbox when the session is available. Now, for those of you watching this session on demand, not right now, but watching the recording, remember to head over to either a Thinkific or GBCI platform to take your quiz with an 80% passing rate, and then you will receive your continuing ed certificates by passing that quiz. For those of you watching the recording of this, for those of you here live today, take that survey that pops up when we close out or is sent to your inbox, especially if you're reporting AIA. And then over the next couple of days, check your certificates for certs at gutenbergcerts.com. Check your spam for that to receive your CU approval. And as always, we need to say a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, all of our over almost 350 members. Thanks to you for supporting us, and our sponsors, especially our top tier gold sponsor, Build Equinox, featuring the GeoBoost system to help add the ventilation strategies to the geothermal. So one of the first questions that came up, you talked about carbon emissions. And so one of the questions that came up is, of course, this need for us to transition to refrigerants that have lower impact on global warming potential, right? We need to get to better refrigerants that do that. And of course, ground source heat pump systems, unless you have an open loop in the water, are traditionally using these refrigerants, which severely have a negative impact on global warming potential and climate change. So within your study, did you consider the transition to less impactful refrigerants within the carbon emissions and geothermal?
It's a good question. In this analysis, in terms of emission reduction, we only account for the avoided on-site combustion related emission. And also we account for the emission in the power generation by reducing the demand. So in that way, we didn't directly account for the impact of this low GWP refrigerant. Yeah, but in the future study, we could account for that by changing the efficiency and also account for the life cycle emission, so that we can also account for the refrigerant itself. Some refrigerant will leak, right? So, yep.
And do you have any general sense of where the ground source heat pump industry is heading with these refrigerants, these more sustainable refrigerants?
Yeah, I think they are all driven by the EPA
Sure.
rulings, right? Now, my understanding is most manufacturers, not only geothermal heat pump manufacturers, in general, HVAC manufacturers doing those kind of things, but most of the refrigerant is R454B, that's dropping refrigerant.
Yeah. Now, I know you're an employee of the federal government in the United States, but we have a lot of listeners who tune in from around the world. Do you sense that this study and this applies to grids across the planet to some extent, or maybe not?
Yeah, I would think the general conclusions of the study can be applicable to other countries. All the countries need heating, cooling. You need improve that efficiency, right? Geothermal heat pump can do it. You need a limited on-site combustion. Geothermal heat pump can do it, right? It's all similar.
Yeah. So a lot of questions came in about the impact on the ground. So some of the questions were, the impact on the soil, the impact on the water, especially if we were to go to this, high level of ground source heat pump adoption, if we were to able to do that, And even I think there's always discussion about at some point if you have too much concentrated ground source, you might be taking too much energy out of the ground and it won't be there. I mean, that's just the extreme kind of where that kind of question goes. So what kind of impact does this have on our environment, our soil, our water? Does it, if there's too much of it, do we lose that energy?
That's also a very good question.
Yeah.
Um, yeah, first I would say U.S. is a very unique situation because in U.S. there are about 130 million single-family homes. Single-family homes means you have a yard. It's not in other country that they all live in those compact, those high-rise building. In that case, your land is limited. If you just extract heat, dump heat, reject heat, you will have significant change. But U.S., I think the impact would be relatively small if you plan properly because geothermal heat pump technically is a passive seasonal thermal storage. That's the reason you have efficiency. In the wintertime, you extract heat, but in the summertime, you dump heat. If you can properly design the system, also integrate with other heat rejection or heat addition, you can get the net energy balance on annual basis, right? That is another way you can mitigate the potential impact. But that question is valid. I know in Sweden, right now, if you want to have a new geothermal heat pumps, you have to get permission because your neighbor already have the geothermal system.
Yeah, sure. Yeah. And yeah, and that was one of the other concerns was just on some of these, and I've heard it too, these tighter, more urban lot lines, just some of the restrictions that are in place, for being where you can kind of drill this equipment. And that kind of leads into like, a personal situation I faced, before I made my transition. My electrification project, I was looking at ground source. And so my options, back in 2019, I think the tax credit had just expired. And just so you all know, the Inflation Reduction Act tax credit now has brought geothermal ground source heat pump tax credits back up to 30 as a starting place, maybe even 50 in low income communities as a bonus, and nonprofits can use the direct pay program to get these monies. So consult your tax advisor. But anyway, when I was doing my project, I didn't have all that, right? This was pre-IRA. So one of the things I had to look at was the horizontal looping, right? It was cheaper, it was less efficient, and it was going to kill a lot of trees, right? And I could go vertical, but that was more expensive, but more efficient. So is your study really assuming everybody's kind of boring vertical at this point, or what?
Yeah. In this study, as I showed in the slides, we are assuming, the vertical ball ground heat exchanger. And also, in our study currently, we don't really account for whether, a particular building have that land, to do those things. That is obviously a limitation of the study. We don't have that resource to check every building, right? But as I mentioned, lots of areas such as New York, Boston, they are developing this community scale geothermal heat pump system, so they can have a common loop. So in that system, your ground heat exchanger may not be close to your building, but it could be somewhere that have empty space, but you can connect them together. So that could be some solutions to address that kind of issue. And in terms of the horizontal loop versus vertical loop, the industry typical practice is vertical loop. Horizontal loop, have some their own pro and cons, right? But the new technology development is to have something in the middle, not complete horizontal, but not also completely the vertical. For example, you can have some underground big tank, that can also serve as a ground heat exchanger. That is my other projects.
Oh, and then there was an additional question here on the map of your ground temps at shallower depths. such as 10 feet. Is that something you all are is there an additional map in your study on that, or?
Yeah. I think recently there are lots of new data sets. I recommend people to check um, Stanford have new data sets. They can tell you the temperature from surface down to maybe 1,000 kilometer,
Mhm.
1,000 meter deep. And yeah, with that tool, this online tool, you can type your address, you can see those stuff. And also even the small conductivity, the values along the depths can also be available. So that is a very, very recent development by Stanford University.
Right.
In terms of yeah, for horizontal design, horizontal loop design, yes, you need not only that temperature at 10 feet, you need the profile because
Mhm.
from 0 to 20 feet, the temperature change, the magnitude reduced along the depths. It's not very constant, but below 20 feet, that's relatively constant. So that is not only just get the 10 feet that temperature, you need to get the profile.
Mhm. Mhm. Well, there are a lot of great questions in here. I don't think we're going to be able to get to all of them. I don't know how much more time you have left. Do you have some time for a few more? Or?
Um, yeah, maybe in four more minutes.
Okay. Well, I saw a good question kind of shifting over to one of the other intention of this study on the transmission and our grid. And, I think about, so you kind of talked about this at a large scale. It really seemed like at a big, a scale when we're talking about like the ISOs or whatever they all are. I know I'm on the MISO grid, um, but going down to the community scale is where their question was coming from. I even think of, you know, people we're working with, they're trying to help buildings electrify in Detroit, and they're like, you can't electrify this building here because you would overwhelm the local street neighborhood grid here, right? It just can't do that. So what kind of impact or opportunity does this have on really the local grid, especially in those communities I think of they're under-resourced and have, poor transmission lines and electrical infrastructure?
Yeah. Um, this in our study, we account for those balance area. In US, there are 134 balance area, right?
Mm-hmm.
That covers, especially maybe cover several states. So it's kind of relatively large scale. To address your questions, we need more granular modeling just for the local grade. This study does not go into that deep. Um, but with this methodology and new data, that can be done, for the local grid.
Mm-hmm. And just to what extent do you all consider the trade-off of air source growing exponentially, which it seems to be, anecdotally speaking, that air source heat pumps seem to have taken off. And I know there's concerns about winter peak load and all of that. Just um, yeah, is that part of the conversation you're having? Is what happens if we, take a different route and go all air source, especially in the cold climate?
Yeah, I would say, the heat pump is good technology. Air source heat pump it's just like the air conditioner. That is
Mhm.
very good technology.
Mhm.
But the different technology have the different advantage and disadvantage, right? The air source heat pump, is much easier to install, but their capacity efficiency could be degraded during very cold weather. Although there are some new cold climate heat pump, but if you look at their efficiency, at cold ambient temperature, it's still low.
Mhm.
And also the cost is also become high. They have to have several compressors or large heat exchangers to get that performance. So in that case, the difference between air source and ground source in terms of cost maybe not that big. So there's just different options, depending on the resource. But this study just indicates, it's not only just from the homeowner point of view, you make your choice between air source and ground source. You also think about if
Mhm.
everybody do the same thing, and how that will affect the grid. So that is something just for people to think.
Yeah. Well, on that note, we'll end it here. And just real quick, where can people go to either contact you or learn more about the study?
Sorry, what's your question?
Oh, the question is where can people go to either contact you or learn more about accessing the study?
Yeah, the report is open to public. There are lots of details in that report, and also yeah, you can contact me if you cannot get your answer from this report.
Yeah. All right, great. Well, Xiaobing, I really appreciate you coming out and all the work that Oak Ridge National Laboratories are doing. So thank you so much for your time, and take care. And thank you all. We'll see you in the next session next week. Goodbye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.